Hello everyone and thank you for watching. I'm presenting our CHI 2026 paper on game-based and gamified robotics education, a comparative systematic review and design guidelines. In this work, we ask a very simple question. When we use games to teach robotics, what kinds of designs are actually being used? What outcomes do they report? And what guidance can we give to educators and system designers? Across this talk, I'll summarize the scope of the review, the three main patterns we found, the research gaps we identified, and the design guidelines and future research directions that emerged from the synthesis. To motivate the review, I want to start with the tension that runs through this literature. Robotics is a powerful way to teach computational thinking, creativity, and systems thinking, but it also has a very steep learning curve. Game-based learning and gamification can make that experience more engaging and accessible. But the evidence base is really scattered. Different studies emphasize different skills, different contexts, different technologies, and different types of measures. So in our review, we asked three questions. What kinds of game-mediated robotics designs have been used, how their outcomes differ, and what limitations and design implications we can derive from the field as a whole. It's worth noting that this is the first systematic review and comparative synthesis of game-based learning and gamification in robotics education. Methodologically, this was a Prisma-aligned review. We searched four major databases, limited the corpus to English language full texts from 2014 onward, and screened the resulting set in different stages. The flow diagram on the right shows the final corpus from 12,485 records. We brought it down to 95 studies which were included in this review. We then coded each paper across a broad feature set, including approach type, learning context, pedagogy, skill level, modality, immersion, and outcomes. An important point is the reliability that we found. Two raters independently classified the different studies, and agreement was very high with a coherence kappa of 0.918. Here we summarize the major findings from this literature review. So this is the high-level overview, and based on these findings, we identified three major patterns, which I'll discuss in the next slides. So the first major pattern is what we call approach context pedagogy coupling. Gamification concentrated in formal settings overwhelmingly, especially classrooms that need clear curricular alignment, predictable assessment, and low integration cost. By contrast, fully fledged game-based learning appeared more evenly distributed and were especially found in informal or extracurricular settings where longer sessions and open-ended play were easier to support. Similarly, pedagogy followed the same pattern. Gamified work leaned towards project-based structures, while game-based learning were more often incorporated with constructivist elements. So the key takeaway from this is that the choice between game-based learning and gamification not just about mechanics, it is also about context and pedagogy. Our second pattern that we found is about the skill coverage. Across the whole literature, the strongest emphasis was on introductory programming and modular kit assembly, which is useful for onboarding, but the pipeline narrows very quickly. Advanced software development was relatively uncommon, and advanced robotic systems work was basically non-existent. One especially important pattern is the disconnect between software and hardware progression. We found that several studies moved towards more advanced programming but did not pair that with comparable systems instruction around sensing, control, integration, or custom hardware. So the literature is much better at getting learners started than at supporting full systems level competence. The third pattern concerns modality and outcomes. The field still relies mainly on physical robots, with simulators as the next most common modality. By contrast, immersive technology such as virtual reality remain relatively rare, and haptics is basically non-existent despite their promise for embodiment and procedural learning. In terms of learning outcome, neither game-based learning nor gamification clearly dominates the other across the literature. Learning gains were broadly comparable and effective benefits were common in both. By contrast, formal settings tended to report measurable gains more often, while informal settings frequently supported interest, enjoyment, and accessibility. So again, we see the similar pattern that the better framing is not either or, but matching the approach to the learning context and objective. So here we summarize where we found the major gaps and where the field is still relatively thin. The most severe gaps are in virtual reality based robotics learning, which is lacking, then the integration of software and hardware skills in a single framework, lack of haptic realism, lack of AI driven personalization, and especially long term skill retention. So this basically means that the literature as a whole right now, the measurement of long term skill retention is severely lacking. These are all areas with strong potential, but the literature is still limited. We also found moderate to severe gaps in the use of transfer measures, meaning whether learning carries over to new tasks and different settings, and in comparative study design, such as multi-arm or factorial experiments that allow stronger conclusions, which were lacking throughout the literature. Finally, statistical power remains a moderate concern since many studies rely on relatively small samples. Overall, we can see that the field is growing, but these gaps show that more rigorous, longitudinal, and technologically integrated research is still needed. Based on the overall literature review, rather than presenting isolated best practices, we organize the evidence into a structured design space and a stage learner progression model. The central idea is that effective game-mediated robotics learning needs alignment between the chosen approach, the learning context, the skill stage, and the evaluation strategy. So for novice learners, that means immediate feedback and visible cause and effect. For intermediate learners, it means scaffolded multi-step integration. And for advanced learners, it means architecture level choices, documentation, benchmarking, and transfer-oriented assessment. The figure on the right captures the full design framework that we present in our paper. So for example, designers should choose the approach with context in mind. Classroom gamification for light integration, richer game-based learning when time and flexibility permit. They should also use hybrid pathways. For example, simulate, build, test, reflect, then iterate. This is to balance the cost, safety, fidelity, and motivation. They should also match mechanics to learner readiness. Onboarding, integration, and systems competence need different tasks, different scaffolds, and different types of assessments. And lastly, the evaluation should move beyond self-report by adding performance analytics, authentic tasks, transfer checks, and delayed post-test. We close with 8 concrete future research directions. Taken together, these directions push the field towards longer-term development rather than short-term engagement alone. We emphasize progression-aware design, inclusive access, stronger multimodal and immersive comparisons, better analytics and delayed assessment, deeper software-hardware co-design, the careful study of AI tools, and scalable interventions for under-resourced contexts. So the agenda is not simply to add more games to robotics education, it is to build learning ecosystems that are adaptive, equitable, methodologically stronger, and better aligned with how robotics expertise actually develops over time. I'll close with 3 takeaways from this whole talk. First, game-based learning and gamification are not opposites. They are complementary design choices whose strengths depends on context and pedagogy. Second, the literature is strongest at the beginner end of the pipeline. It does a great job motivating learners and introducing core programming concepts, but much less work supports advanced integrated robotics expertise. And third, the most promising next step is to design progression-aware, inclusive, and hybrid systems, and to evaluate them with stronger methods than short-term self-report alone. So that is the end of my talk. Thank you for your time and patience.